This is a problem on the conservation of mechanical energy, and as a quick refresher, mechanical energy includes kinetic energy and all forms of potential energy. So it's a subset of total energy, which includes things like heat and internal energy, which oftentimes we don't have to worry about, or we don't want to worry about in a problem. So instead of using total energy, we use a subset, which is mechanical energy. And here we're going from kinetic to gravitational potential energy. So the problem says a ball is launched straight up into the air at 11.5 meters per second. How high up does the ball go? Then it asks, how high would the ball have gone if instead it had been launched at a 53.8 degree angle? So that's what we want to find if it had been launched at this angle instead of being launched straight up. And then it says, assume there is no air resistance. So when you have that sentence, no air resistance, that means you can use the conservation of mechanical energy. Remember, mechanical energy is not conserved in the presence of friction. Okay? So, in the beginning, or initially, what we have is this ball being launched straight up, right, with some velocity of 11.5 meters per second. And that's at some moment in time, which we'll call the initial moment. And then later in time, it's sitting here at the top, and it's been elevated by some height, h, and the velocity at this moment is 0. So let's call this on the left the initial moment, and on the right, it's the final moment. All right, final. And let's just say that over here on the left, initially the height is 0. Let's set this height as the 0 position from which we will measure all heights. And that's important because the 0 height is arbitrary. That just means we get to choose what's the 0 height. So let's say I'm standing on the roof of a building, I could say that I'm holding a ball out in my hand at a height of, well, I could say that the ball's height is 1.5 meters above the top of the building. Or I could say the ball's height is 21.5 meters from the ground below. So what we take as the 0 height, or the 0 level, is arbitrary. And so we select that level to be convenient. We select it so that it's convenient. And if we take this initial height here as the 0 level, here's why that's so convenient. Because the gravitational potential energy will be 0 initially. So all the ball will have is kinetic energy, 1/2 mvi squared. Over on the right, once the ball has reached this new height, it will have no velocity, 0 velocity, so Ke will be 0, and all of its energy will be gravitational potential, mgh final. So in these problems, you always draw a picture. That's the best way to start. And in the picture, you show what the energies are. So initially, there's no gravitational potential. The kinetic is 1/2 mv squared, and there's the velocity. Finally, at the end, there's no kinetic, v is 0, and the gravitational potential is mgh. In the conservation of mechanical energy equation, you tally up or just add together all of the initial energies on the left side of the equation, and you add all of the final energies on the right side of the equation. So on the left we have 0 for Pe, and we have 1/2 mvi squared. And on the right, our energies are 0 for kinetic energy plus mgh, where h is the final height the ball reaches. And that's what we're asking, that's what we're solving for, is the final height. So you look and you see, oh my gosh, we don't need the mass. How convenient. They cancel, right? The mass here cancels with the mass here. And that's pretty convenient because we weren't even given the mass, so it had to cancel. Now we look and we see that the initial velocity is squared divided by 2, right? So vi is, where is it, 11.5. That is equal to 9.81 times the final height. So you solve for the final height by dividing left and right by 9.81, And what do we get as our answer? 0.5 times 11.5 squared over 9.81. 6.74. That's the height. And that's in meters. There you go. Very good. 6.74 is the height. And let me make that actually a 6. Good. The next thing it says is find how high it would have gone if it hadn't been launched straight up, but instead if it were launched at this angle. Okay, well let me erase what I have here. So now we have this picture. The ball is like this, being launched at 11.5 meters per second at this angle, right? So on the left side, it will have kinetic energy, which is going to be equal to 1/2 mv squared, And will it have any gravitational potential energy? Well, no, because we're going to just say that the ball is being launched from the 0 position. Right? So imagine it's being launched from the ground or something, whatever you want the 0 position to be physically. Alright, well, we're letting this initial height be 0, which means the initial gravitational potential energy is 0. And then the ball flies up into the air and it reaches its max height. Right? And when it reaches its max height, let's draw in the max height, h final. Is it completely stopped moving? No, it's not. There's some x component to the initial velocity. And that x component, let's call it Vx, the ball still is moving with that x component of the velocity. So the ball is moving forward with some velocity Vx when it reaches the final height. Right? Because gravity can only slow down, it can only decelerate the y component. The x component of initial velocity is unchanged, and the ball continues traveling with the same x component of velocity the entire time it's in the air. That means that we're going to have gravitational potential energy, mgh, whoops, so let me write in mgh, and we'll also have some kinetic energy, which will be 1/2 mvx squared. There we are, like that. Okay, so now we go to our mechanical energy equation, our conservation equation, and we tally up, we add together all of the initial energies, and we put those on the left side of the equation. Then we tally up or add together all of the final energies and put those on the right. Okay, initially there's 0 for the gravitational potential, and there's 1/2 mv squared for the kinetic, and then at the end, in the final moment of time, what we're considering the final moment, which is this, what do we have? We have gravitational potential, so there's mgh, and there is the kinetic 1/2 mvx squared. And just like before, the great thing is that the masses cancel. That's expected because we weren't even given the mass in the problem, so they better cancel. Okay, we can plug in 1/2 times the initial velocity, right? This is really vi. So we plug in the initial velocity, which is 11.5 squared. Don't forget the squared. That's a common mistake in the high school physics classes, is forgetting to square your value of velocity. And on the right, we have 9.81. The final height is what we're solving for. And I'm running out of room, so I'm just going to say plus 1/2 Vx squared. And of course, the x component of initial velocity, well, if we know the angle, the bottom angle with the x-axis, and so we know the bottom angle here, we know how much the initial velocity is. The x component is just 11.5 cos 53.8. 11.5 cosine 53.8. And I'm running out of room. There we go. 11.5 cosine 53.8. And again, just in case we forgot why that's true, if this is the initial velocity, and this is the x component, and that angle right there, if that angle is at 53.8, well, we could draw the y component, and you see that the cosine of 53.8 is Vx over Vi, which Vi is 11.5. So if you multiply both sides of this equation by 11.5, you see that Vx is equal to what I've written in, 11.5 cosine 53.8. Good. So we solve for the final height, and that comes to this. You have to subtract this from the left and the right side before you do anything else. Then once you've subtracted this from the left side, you calculate the left side and divide it by 9.81. So this is going to come to 0.5 times 11.5 squared minus 0.5, open parentheses, 11.5 cos 53.8, and then close all the parentheses. And then you can actually just hit enter and then divide the answer by 9.81. And what do we get? We get the final height. Oops. The final height comes out to be 6.39 meters. So that's interesting. It's significantly less, right? It is less than if we just launched it straight into the air, which is what we expect. That makes sense in terms of our everyday life. If you launch something at an angle rather than straight up, then it's not going to go as high. So that's what this says. And that's how you solve.